Let's talk about some important things to remember about eigenvalues and eigenvectors. Let's talk about some observations about eigenstuff. It's not really an observation. This is actually summarized in a theorem, but here's the big one. Distinct eigenvalues correspond to linearly independent eigenvectors. Distinct eigenvalues correspond to linearly independent eigenvectors. Notice that in the first example that we did, that 2 by 2 matrix A, we had eigenvalues of 3 and 5. 3 corresponded to the eigenvector -1, 2, and 5 corresponded to the eigenvector, what was it? Wrong way. Corresponded to the eigenvector -1, 1. Those eigenvectors, they corresponded to distinct eigenvalues, and the eigenvectors were linearly independent. So for example, lambda equals 3 and lambda equals 5, and lambda equals 5 are distinct eigenvalues, and they correspond to linearly independent eigenvectors. -1, 2, and -1, 1. Yeah, -1, 1. I'm just trying to be consistent. I could have called it 1, -1. The important thing is that these two eigenvectors are linearly independent, and we knew that they would be because they correspond to distinct eigenvalues. Distinct just means they're not the same. We also saw in matrix B, for matrix B, we had distinct eigenvalues and they corresponded to linearly independent eigenvectors. So change pages. We had lambda equals 1 and -2. Lambda equals 1 and lambda equals -2 are distinct eigenvalues corresponding to linearly independent eigenvectors. And the vectors for lambda equals 1, we got 1, -1, 1. And for lambda equals 2, we got 2 linearly independent eigenvectors. -1, 1, 0, and -1, 0, 1. This first one is for lambda equals 1, and these second two are for lambda equals -2. Distinct eigenvalues correspond to linearly independent eigenvectors. The number, an n by n matrix A will have a degree n characteristic polynomial. So an n by n matrix A will have a characteristic polynomial I didn't need to name the matrix, I guess. An n by n matrix will have a degree n characteristic polynomial. That means that we will have, counting multiplicities, n eigenvalues. So an n by n matrix will have n eigenvalues counting multiplicities. An n by n matrix will have n complex eigenvalues counting multiplicities. So now we have to remember some stuff about polynomials. So we have to think back to polynomials. If we have a polynomial with rational coefficients, then irrational zeros will come in conjugate pairs, and complex zeros will come in conjugate pairs. So recall about polynomials. A polynomial with rational coefficients if it has complex zeros, I didn't write this sentence very well. If a polynomial with rational coefficients has complex zeros, then they come in conjugate pairs. Ugh, I hate that sentence, but all right. If a polynomial with rational coefficients has complex zeros, then they come in conjugate pairs. That is, if there's a plus bi, then there's a minus bi. If a polynomial with rational coefficients has irrational zeros, then they come in conjugate pairs. No, leave that part off. Just stick with the first one. My bad. So, if a polynomial with rational coefficients has complex zeros, then they come in conjugate pairs. I was thinking about something else for that last one. So, we also have to think about this multiplicities business. What that means is that the determinant, if we look at example matrix B as an example, the determinant of B minus lambda I equals 0, this determinant is a third degree polynomial. It's a degree 3 polynomial equation with integer coefficients. What we found out was that the zeros were only 1 and negative 2. It's got integer coefficients. The zeros are 1 and negative 2. Oh, it's an equation. Solutions. We only have 2 distinct solutions. We expected there to be 3, so one of them must be repeated. We ended up with 2 distinct solutions, But since it's a degree 3 polynomial, we expect 3. Three, counting multiplicities. So the three solutions are either 1, 1, and -2, or 1, -2, and -2. So it's either 1, 1, -2, where 1 has multiplicity 2, or 1, -2, -2. It could be the -2 has multiplicity 2. That is, the determinant of b minus lambda I is either lambda minus 1 squared times lambda plus 2, or lambda minus 1 times lambda plus 2 squared. This is just thinking about polynomials, because I know we remember everything about polynomials from pre-calculus. Which one must it be? Based on what we've seen so far, I haven't told you how this works, but which one must it be? Is it lambda equals 1 has multiplicity 2, or is lambda equal -2 multiplicity 2? Which of these eigenvalues has multiplicity 2 based on what we know? Based on this information. Which one of these eigenvalues has multiplicity 2? One vote for -2. Any others? Anyone want to go with anybody on team lambda equals 1? Is there anyone on team lambda equals 1 just because I go, he didn't just say yes? If you're on team lambda equals 1 just because I didn't say yes immediately to lambda equals -2, then you're just trying to be contrary and you're metagaming. Don't do that. Some of you are trying to metagame on the quizzes. But I made a typo in transferring my paper quiz to the Canvas quiz. So your solutions were wrong because you solved the wrong problem. So it is lambda equals -2. And we can see that because lambda equals 2 corresponded to a two-dimensional eigenspace. So it's this one. Lambda equals -2 corresponded to a two-dimensional eigenspace. And we can do that if we find the characteristic polynomial for the matrix B with some kind of online calculator. Any questions? When I give you the eigenvalues of a matrix, I don't tell you the multiplicities. I want you to find that out for yourself. So here's another important thing to remember. And this will get us into our last thing for today. An eigenvalue with a multiplicity of 2 could correspond to a two-dimensional eigenspace, or it could correspond to a one-dimensional eigenspace. We don't necessarily get as many eigenvalues as the multiplicity of the we don't necessarily get an eigenvector for each multiplicity. Writing this in English is very difficult, especially at 10:30, where I'm barely conscious anymore. So we don't always get a linearly independent eigenvector for each multiplicity of the eigenvalue. If the eigenvalue has multiplicity, let's say n, the corresponding eigenspace is at most n dimension. the dimension of the corresponding eigenspace is at most n. At most. So the eigenvalues, lambda equals -2 has multiplicity 2. The corresponding eigenspace might be 2-dimensional or 1-dimensional. It turned out to be 2 in this case, but if all we know is that the has multiplicity 2, it could be 2 or 1. It was dimensional, 2-dimensional for the matrix B. Any questions? That meandered a little bit because I started thinking about polynomials. No, we could not have a 3-dimensional eigenspace if the multiplicity is only 2. The multiplicity is the largest dimension of the corresponding eigenspace. All right. Let's think about, let's talk about why we care about this. Let's actually pause the video here and then think about why we care about this.